Bismillah ar-Rahman ar-Rahim. By the name of God, most merciful, most kind. Peace be upon you and God's blessing. We are going to discuss solve problem 5.1 from the Unified Design of Steel Structures Handbook. The solved problem 5.1 is common in the third and in the fourth edition of the Unified Design of Steel Structures book. The content of the solved problem 5.1 is the case of column to check whether it will buckle before yield or not, and the given section is W10 by 33, where 10 is the depth of the W section, while the 33 is the bound per linear foot. The height of the column is 20 feet, and that column is bent from both sides in both X and Y directions. The type of steel is A99-2 steel, which means that the yield stress of that column is 50 KSI. We'll move to the next slide. In the next slide, we have a graph for which the horizontal axis LL sub C over R, which is KL over R. And the dotted line is the Euler stress, which is represented by F sub E equal to pi squared E over KL over R all raised to the power of 2, or can be modified based on the specification as pi squared E divided by L sub C over R all raised to the power of 2. In order to check whether the column would theoretically buckle prior to yielding or not, in the Y direction, we will get the critical stress by KSI, and this is the Euler stress. For the yield stress for the given A99-2 steel, we have F yield 50 KSI. What we are going to do is we will draw the graph, and we will move at F yield equal to 50 KSI horizontally until we hit the graph, and then find out the value of L sub C over R. How can we do that? We are going to check. We're going to write the F sub E equals to F yield equal to pi squared E over KL over R all squared. We'll put on the left hand side the critical stress as 50 KSI, pi squared multiplied by 29,000, which is the elasticity, modulus of elasticity. But we are going to readjust the term. 50 will come here, and the KL over R or L sub C over R all squared will come to the left hand side. We are going to get that L sub C over R squared equal to 5,724.36. When we take the square root of both sides, we get L sub C over R 75.65. So it means that when we have F yield 50, we are going to find out that L sub C over R equal to 75.64. We move to the next slide, in which I have used an Excel sheet to draw the Euler graph, but I make extract of the graph for F sub CR from 0 to 300 and divide it to this major axis into 50s. For F yield equal to 50, and this is the graph, and the x-axis is L sub C over R, we can find out that for F yield equal to 50, we get the horizontal value very close to 80, which is 75.65. Okay. We check the solved problem 5.1. The goal is to determine the theoretical strength of the bend-ended column and whether it will first buckle or yield. This is table 1-1 for the W section. Our section is W10 by 33. From part 1 of table 1-1, we have W10 by 33. There is no C footnote, which means that this column is not cylinder, and we can get all the necessary information we need. First part will give us the gross area of the column as 9.71 inches square. By the way, this solved problem 5-1. Again, it is in the 3rd and 4th edition in the Unified Steel Design book. For the second part of table 1-1, we are going to get R sub x, R sub y, Ix, and Iy, as we are going to see. Here is table 1-1 in the second part. The Ix value, we get it from here as 171. R sub x is 419. And for I sub y, it is 36.6. And R sub y is 194. We are going to examine the buckling about the x. This is the W shape, and this is a major x as xx, and this is a minor x, y. When we are saying that we are this column have a buckling about the xx, it means that it is same like the beam, which is under flexural bending. It will move bending about xx. It means that we have bending about the measure xx accompanied by a movement in the y direction. This is a movement in the y direction. If we have a look from here, we'll find these two edges of the flange at the right and left side, and this is a web plate can appear like that. For the L sub C for x, it is equal to the KL in the x direction. We have bend end, which means that we have K effective factor, K equal to 1, and the column height is 20 feet. We multiply K by L. We have 20 feet. When we multiply by 12, we have 240 inches. R sub x from table 1-1 is 4.19 inches. We have two options to solve that problem. The first option is to determine L sub C over Rx in the x direction and L sub C in the ry direction. We take the bigger value out of these two values. Then we are going to refer back to the Euler graph and check whether the bigger value of L sub C over Rx or L sub C Ry bigger or smaller than the corresponding LC over I for the yield stress 50 or not. This is our first step. L sub C over I is 240 over 4.19. It will give us 57.27. For the second option of solution, the author, he has determined the load in the X load and the Y, and then he selected the smaller load and compare it with the load due to yielding. We need to estimate the Euler stress in the X direction. We have E equal to 29,000 KSI, and by is 3.14159. By squared E over 240 divided by 419 all squared will give us stress 87.24 KSI, which is apparently larger than the yield stress, that is 50 KSI. But we have to check in the Y direction. That's why we will move to the next slide. In the next slide, we have the same K equal to 1 bend end both, and the K, the height is 20. This is a section. This is a minor X, YY. This is a major X. When we are saying we are buckling about Y, as if we are moving in the X direction, so we are moved like this. If we have a look, if we make a cut, we will find out that this line, dotted line, is for the web section, and this is the right edge, and this is the left edge. From table 1-1, in the second part, we get R sub y equal 1.94, L sub y equal to 240 inches. So LC over RY is 240, but divided by 1.94 will give us 123.71, which is larger than the LC over R in the X direction. And basically, the corresponding Euler stress, critical stress, is 3.14159 squared by 29,000 divided by 123.71 squared will give us 18.70. This is stress is below the previous Euler stress for X-axis. In the next slide, we will go back to the graph. This is the graph which we have already discussed. This is the Euler graph, LC over RY. We have already 75.64 L sub C over R. This is the X. We have LC over Rx is 57.27, will give us higher stress than the 50, while in the Y direction, we have L sub C over Ry 123.71, that will give a stress smaller than the yield stress. We are going to select the higher value, which is 123.71, that will give us stress, lower stress. The answer for the requirement, since this zone is at the right side of the L sub C over Ry that belongs to the yield, this is higher than the 75.64, it means that the column will buckle, will have theoretical buckling prior to yielding. Based on the author's solution, the author, what he has done, he multiplied the stress by the gross area in the vertical axis. That's why the relation is between the load and the L sub C over R. This is L sub C over R, and the vertical axis represents the load, and this is the same graph. So for the yielding at 50 KSI will give us a load equal to the gross area multiplied by F yield. The gross area is 9.71 from table 1.1 part 1, while the yield stress is 50, multiplying both will give us 485.5 kips. And these are the two loads. One load due to L sub C over Rx. This is a higher stress than 50 in the X direction. 90.71 by 87.24, this is the stress. And for L sub C over Ry, this will give us stress equal to 18.70. When we multiply by the gross area, will give us 181.577. We take the smaller value, which is almost 182. Since this is the load now, the load is 182, is smaller than the yield load, which is 485.5, then again the same result, the column will have theoretical buckling prior to yielding. And here the last slide. This is if you are going to check by taking the minimum Euler stress, minimum 18.7 or 87.24, it is 18.7 multiplied by the gross area will give us 182, approximate value 182 kips. We have come to the end of our solved problem 5-1. Thanks a lot and see you. Goodbye.